particle physics, huh? Not exactly beach reading material.
Well,
But this paper you sent me, uncovering the root of LEFT and SMEFT. Oh man, it's like a treasure map, right?
yeah.
We're talking about potentially rewriting physics textbooks here, aren't we?
Yeah, I mean, you're spot on. It's like having a backstage pass to
No
the
cues.
biggest physics experiments happening right now.
And you've got the guidebook, so walk us through it. What is the big idea behind this paper?
Okay, so imagine you're a detective, right?
Okay.
You're at a crime scene. You've got clues, but they only tell you so much about what actually went down.
Right.
That's where this research comes in. It's all about connecting the dots between the clues we can see in particle physics, things like rare particle decays, and the potential culprits, new particles, forces that we haven't even discovered yet.
Okay, I'm intrigued, but we're talking about the subatomic world here. Like, how do you even begin to investigate something that small?
That's where these things called effective field theories, or EFTs, come in. Think of them like powerful microscopes that let us zoom in on the universe at different energy levels.
Gotcha, like different lenses for different magnifications.
Exactly.
So what lenses are we using in this case?
This paper focuses on two, LEFT and SMEFT. So LEFT, or low energy effective field theory, that's like our everyday lens.
Okay.
It helps us make sense of particle interactions at the relatively low energy levels we're used to observing.
Okay, so lefty is for the here and now of particle physics. What about SMEFT?
SMEFT, or standard model effective field theory, that's our high-powered electron microscope. It kicks in when we need to study, really high-energy collisions like the ones happening at the Large Hadron Collider.
So we're using LEFT and SMEFT to look for clues about new physics, but what kind of clues are we talking about, like, specifically?
We're looking for things that break the usual rules of the standard model, things that would make a physicist shout, "Eureka," from the mountaintops.
Okay. All right, you've got me on the edge of my seat. Give me an example.
Well, remember those baryon and lepton numbers you learned about back in Physics 101?
Vaguely. Refresh my memory.
Okay, so every particle has a baryon number, represented by B, and a lepton number, L. In the standard model, these numbers are usually conserved.
Right.
It's like a cosmic balancing act.
So what happens if the scales tip? What if these baryon and lepton numbers aren't conserved?
That's where things get really interesting. See, this paper suggests that violations of B and L conservation, while incredibly rare, could be our most promising window into physics beyond the standard model.
Okay, so B and L violations are clues, but we need something to connect them to the bigger picture, right?
And that's precisely what the authors of this paper have done. They've created a sort of map, a network, that links these B and L violating processes to specific types of new physics at higher energy scales.
Hold on, how do they even create a map of something we haven't discovered yet?
It's all about these things called operators, which are essentially the mathematical terms that describe different types of particle interactions.
Operators, like verbs, they tell us how the particles interact.
Precisely. And the authors categorize these operators based on their dimensions, which relate to their energy levels, and how much they violate B and L. Think of it like charting constellations, but for particle interactions.
So if we see a specific type of B and L violation at a lower energy, we can follow this map to see what kind of high-energy physics might be causing it?
Exactly. It's like having a cosmic decoder ring.
Whoa.
And the implications are huge because some of these potential culprits are, well, mind-blowing.
Do tell, what kind of culprits are we talking about here? What kind of physics could be lurking in the shadows?
Let's save that juicy bit for after a quick break, shall we?
All right. No more cliffhangers. You were about to tell us about the potential culprits behind these B and L violations. What kind of mind-blowing physics are we talking about?
We're diving headfirst into the realm of beyond the standard model physics here.
Okay, that sounds big. For those of us who need a refresher, what is the standard model and why do we need to go beyond it?
The standard model, it's like our physics periodic table.
Okay.
It's incredibly successful at explaining the particles and forces we know and love, but it leaves some big questions unanswered.
Like what? Spill the cosmic tea?
Well, for one, it doesn't explain dark matter or dark energy.
Right.
Which together make up a whopping 95% of the universe.
Huge.
Yeah. And don't even get me started on why neutrinos have mass when the standard model initially said they shouldn't.
Right.
Yeah.
So there are some gaps in our understanding, and this paper, this map they've created, it's pointing us towards what might fill those gaps.
Exactly. By studying these B and L violating processes, we're essentially looking for cracks in the foundation of the standard model, places where new particles or forces might be revealing themselves.
Okay. Okay, I'm picking up what you're putting down. So what do these cracks lead to? What kind of exotic particles or interactions might be causing these violations?
Fasten your seatbelts. We're about to get weird. We're talking about things like proton decay, where a proton, one of the fundamental building blocks of matter, just spontaneously falls apart.
Wait, protons can just do that. Disappear.
That's what we're trying to find out.
Yeah.
It's never been observed directly, but this paper suggests it could be happening at an incredibly slow rate, perhaps taking billions of years.
Mm.
And if we could detect it, oh man, it would be a huge win for certain beyond the standard model theories.
Okay, proton decay, that's one for the books. What else?
How about neutron-antineutron oscillations? Picture a neutron just chilling out, being itself, and then suddenly, poof, it morphs into its antimatter counterpart, an antineutron, and then back again.
Whoa, that's some next level quantum weirdness.
It is. And then there are things like rare decays of nucleons, which are the particles that make up the nucleus of an atom, and this really wild process called neutrinoless double beta decay, which involves two neutrons transforming into protons without releasing any neutrinos.
Okay, my brain is officially a little fried, but in a good way. So we've got this whole menu of potential B and L violating processes, each weirder than the last. How do we even begin to look for this stuff?
That's where the real excitement comes in. This paper doesn't just highlight the mysteries, it gives us a strategy for solving them. It tells us what specific signals to look for in our experiments, both at low energies and at the high energy collisions happening at places like the LHC.
So it's like the authors are saying, hey, if you want to find new physics, here are the breadcrumbs, follow the trail.
Exactly. And the best part is with this map they've created, we can start connecting the dots between seemingly disparate observations.
So a rare decay we see in a low energy experiment could actually be hinting at the existence of a completely new particle or force at much higher energies.
Precisely. And that's incredibly powerful because it gives us a way to test these beyond the standard model theories that would otherwise be incredibly difficult to probe.
This is blowing my mind, We're talking about potentially rewriting like the laws of physics as we know them.
That's the beauty of fundamental research, right? It has the power to completely upend our understanding of the universe.
So where do we go from here? I mean, are scientists actively using this map right now to guide their search for new physics?
Absolutely. This paper is already having a major impact on experimental design. Knowing what specific B and L violating processes to look for, it helps physicists decide what kind of detectors to build, how much data they need to collect, what energies to probe.
So it's like having a more focused lens for observing these incredibly rare events.
Exactly.
Yeah.
And that's crucial because we're often talking about finding, a single tiny anomaly hidden in the sea of data.
So it's not just about looking for new things, it's about knowing how to look for them.
Precisely. And that's what makes this research so groundbreaking. It's giving us a much, much clearer path forward in what can sometimes feel like a very, vast and mysterious field.
It's like the difference between wandering around in the dark and having a flashlight.
Right?
To guide your way.
Yeah, I like that analogy. And the more we understand these B and L violating processes, the brighter that flashlight becomes.
So what's the ultimate prize at the end of all this? If we manage to pin down these violations, if we find definitive proof of physics beyond the standard model, what changes? Like for us, for our understanding of the universe?
That's the million-dollar question, isn't it? It could revolutionize fields like cosmology, astrophysics, maybe even energy production. We could be talking about everything from a deeper understanding of the Big Bang to new sources of clean energy.
No, that's a future I can get behind. But let's be real for a second. This is heavy stuff. If someone's listening to this and feeling a little lost in the quantum weeds, is there a way for them to stay up to date on all this without needing a PhD in particle physics?
Absolutely. There are some fantastic science communicators out there doing incredible work to make these complex topics accessible to everyone. Follow some blogs, check out YouTube channels. Even just reading popular science articles can give you a great overview of the latest discoveries.
My advice, find those people who can explain things in a way that clicks for you.
Yeah.
And don't be afraid to ask questions. Curiosity is the fuel of scientific discovery.
I couldn't agree more. And honestly, the fact that you're even curious about this stuff puts you ahead of the game. Particle physics isn't always easy to wrap your head around, but it's worth the effort.
Because it's about understanding, like, the fundamental building blocks of our universe.
Yeah.
It's about uncovering the secrets of how things work at, like, the deepest level.
And that's a journey that belongs to all of us. Whether you're, a seasoned physicist or just someone with a curious mind, every new discovery brings us one step closer to understanding our place in the cosmos.
So there you have it. From muon decays to proton oscillations, we've journeyed to the very edge of known physics. And the most exciting part is, we're only just beginning to scratch the surface.
The future of physics is brimming with possibility, and I, for one, can't wait to see what mysteries we uncover next.
Thanks for joining us on this deep dive into the subatomic world. Until next time, keep asking questions and never stop exploring.